Hello everyone, my name is Zhong. In this time, one of my research paper, the title of Optoacoustic Quantitative in Virtual Detection of Diabetes mellitus involving the comprehensive impacts based on the improved quantum particles Zhong optimized wavelength linear network was nominated by the International Research Awards on New Science Inventions. I'm very fortunate to have won the Best Researcher Award. I'm very grateful for the International Research Awards on New Science Inventions. Now I introduce myself. My name is Zhong. I'm a doctor, I'm a professor, and I'm an outstanding young talent in Jiangxi province. I'm the lecturer of Nanchang Key Laboratory of Photoelectronic Detection and Information Processing. I'm also a lecturer evaluation expert of the National Natural Science Foundation of China. I'm also a member of China Optical Society, a member of China Optical Engineering Society, and a member of Jiangxi Optical Society. I graduated from the School of Mechanical and Electronic Engineering at Nanchang University in 2017 with a doctoral degree. I have worked at the Provincial Key Laboratory of Optical Electronics and Communication at Jiangxi Science and Technology Normal University since July 2006, and I was promoted to the title of professor in 2020. My research focuses on the optical electronic and its application in biophotonics, medicine, optical electronic detection, and artificial intelligence information processing. At present, I have presided over more than 20 national, provincial, municipal, and department-level science and technology projects, including 3 international natural science foundations, 1 key natural science project in Jiangxi province. Up to now, I have published over 17 SCI and EI indexed papers and authorized 13 invention patents. Now, I will introduce my paper. The title is Optoacoustic Quantitative in Virtual Detection of Diabetes mellitus involving the comprehensive impacts based on the improved quantum particles Zhong optimized wavelength linear network. This work has already been published in the Junior International Journal of Optoelectronics. Now I first introduce the abstract of this paper. The high accuracy detection of blood glucose level is very important for non-invasive monitoring of the diabetes mellitus. In this work, the optoacoustic quantitative in virtual detection of diabetes mellitus involving the comprehensive impacts of multiple factors were first established. To achieve this, a set of OA in virtual detection system of blood glucose with the comprehensive influence of 5 factors were constructed. The real-time OA signals of 625 lab beats for blood were obtained at the characteristic wavelength of 750 nanometer, as well as peak-to-peak waves. Results show that the accurate detection of BGL was very difficult due to the complicated OA signals. To accurately predict the BGL under the comprehensive impact of 5 factors, wavelength linear network were employed to train BGL of 500 training cell blood. The mean square error of BGL for 125 testing cell blood was 6.5782 micromole each letter. To decrease the MSE, WM optimized by quantum particles Zhong optimization, that is QPLS, WM organisms organized. The MSE of the BGL based on the QPLS WM was 0.37485 micromole each letter, which was superior to 0.48005 micromole each letter of PSOWM. Particularly, to further decrease MSE, a non-dynamic screening age coefficient strategy was proposed and compared with other 4 kinds of DSC strategies and the fixed one. With the optimal parameters, the MSE of the BGL was decreased to 0.3088 micromole each letter. Comparison results of 7 algorithms and research works demonstrated that OA technology combined with QPSOWM algorithm and the lower non-linear DSC strategy has excellent performance in the quantitative detection of diabetes mellitus involving in the comprehensive impacts. Now I will introduce why we started the research of this article. As we know, the diabetes mellitus is a chronic disease with endocrine disorder. It has also already become the second biggest killer after cancer. According to the WHO reports, there will be over 0.7 billion of diabetes patients in the world in 2045. The number of deaths from the diabetes and its complication is approximately 5 million over the world every year. So the situation of the country and treatment of diabetes mellitus is imminent. But unfortunately, there are currently no any specific drugs can be used to cure the diabetes mellitus, except hypoglycemic drugs and insulin used to control blood glucose in human body. Nevertheless, this reasonable control of diabetes mellitus requires the accurate monitoring of blood glucose level. Therefore, the accurate and stable measurement of BGL is an essential task treating the diabetes mellitus. Up to now, there are different methods can be used to measure the blood glucose. That is, for example, the traditional method. For this method, the blood should get by punching a finger or joint from a vein. Then the blood was analyzed by the biochemical analyzer or the blood glucose meter. For the traditional method, it is destructive to the biological tissue. It not only brings an enormous economic, physical, and mental burden, but also it increases the risk of secondary infection because of skin damage. So the non-invasive detection technology will be the developed trend in the future. For the non-invasive technologies, there are several non-invasive technologies can be used in now. That is new infrared spectroscopy, middle infrared spectroscopy, Raman spectroscopy, and polymerizer technology, etc. For this spectroscopy method, the advantage of this method is it is non-invasive, rapid, and convenient. But the disadvantages of this method are very obvious. That is, their accuracy and reliability are limited by the problems of tissue scatter lines, spectral overlaps, and strong optical absorption of water, etc. In this study, novel and we are promising a non-invasive technology was used, that is optoacoustic technology. The advantage of the optoacoustic technology is it has higher accuracy and stability because it combines the advantages of pure optical and the advantage of pure ultrasonic. At the same time, it overcomes the interference of each tissue scattering light because of the captured ultrasonic waves instead of the photons. Although the optoacoustic technology has a unique advantage in the non-invasive detection, some factors inevitably affect the optoacoustic detection blood glucose. Some researches on the influence of the blood glucose optoacoustic detection have already been studied by some scholars. However, up to now, the comprehensive influence of multiple factors on the optoacoustic detection of blood glucose have not been intensively studied in the world. In addition, with the development of the informatics technology, more and more artificial intelligence methods have already been into the data analysis and processing in the biomedical fields. And for the informatic analysis and diagnosis of diabetes mellitus, some artificial neural network algorithms have widely used in recent years. So in this work, the comprehensive effect of multiple influencing factors on the OA detection of blood glucose will firstly studied. For our invention detection in system of blood glucose for rabbits whose blood was constructed. In the system, 5 different influencing factors including radiation, energy concentration, temperature, flow rates, and vessel depth were considered. For each influencing factor, different levels will measure the optimal characters. Absorption waves of blood glucose will determine under the optimal characteristic waves the real-time optoacoustic signals and ppbs for 625 or blood specimen of 125 rabbits will obtain corresponding to 625 groups of combination cases of 5 influence factors. Then to get the accuracy, qualitative prediction of BZA under the comprehensive influence of 5 factors, WNN was employed to build the quantitative prediction model of the BZA for 500 test training set blood of 100 rabbits with 5 influencing factors. And mean square error, that is MSE, was used as the evaluation criterion to decrease the MSE of BZA. The QPSO algorithm was employed to optimize the parameters of WN, including the weight, learning rate factors, scaling factors, and shifting factors of a candidate wavelet basis function. That is, QPSO WN algorithm were used. In particular, to further decrease the MSE of BZA, a novel dynamic shrink coefficient strategy of QPSO algorithm was proposed in this work. The MSE values of the novel nonlinear DSC strategy we obtained at different coefficients and compared with the fixed coefficients and the other 4 kinds of DSC strategies. That is, linear strategy, second-order strategies, quadratic polynomial strategies, and power exponent strategy. The better performance of QPSO WN algorithm with the lower nonlinear DSC strategies was presented, and the effects of iteration number of training number on the MSE of prediction BZA were also investigated with the optimal parameters. The satisfactory MSE of predicting BZA for 125 testing set blood of the other 25 rabbits we obtained. The comparison results of 7 algorithms demonstrated that the QPSO WN algorithm with the lower nonlinear DSC strategies is superior to the particle least square regression, that is PLSR, BP linear network, particle swarm optimized BP, that is PSO BP linear network, WN, PSO WN, and QPSO WN algorithms. In this study, a set of the optoacoustic detection system of the blood was constructed. That is shown as follows. And the 5 influence factors were configured. For the irradiation energy, there are 4 different values were used. That is 0.15 microjoule, 0.26 microjoule, 0.37 microjoule, 0.49, and 0.62. For the concentration, there are also 5 different concentrations we will use. That is 2, 5, 8, 11, and 14 micromole each letter, which corresponding to different Stamis degrees. That is hypoglycemia, the normal and slight diabetes, the moderate diabetes, and severe diabetes. For the temperature, there are 5 different temperatures were used. That is 34, 36, 38, 40, and 42. For the flow rates, there are also 5 different flow rates were set. That is 0.057, 0.099, 0.145, 0.184, and 0.219. For the vessel depths, there are also 5 different values were used. That is 1.5, 2, 2.5, and 3 micrometer. And the real time, the optoacoustic signals for the different glue cross with different concentration and different irradiance wavelengths were obtained, which are shown in the figure 6. And the optoacoustic PPBS spectra from the 700 to the 1064 nanometer were also obtained. In order to get the optimal characteristic waves of the blood glucose, the interval PLSR model were used. From the figure 8, A and B, you can find that the optimal wave bands from the 740 and to the 775 are the best. And from the figure 8, you can find that the correlation coefficient of the ASF model for the wavelengths of 715 nanometer is the highest than most of others. Therefore, 715 nanometer is determined as the excitation wavelength of the OPO pasta laser in these experiments. And then the effects of influence factors on the real-time OA signals of blood glucose were obtained. and the comprehensive effects of influencing factors on the OAPB-VS of blood clots were obtained. And in this study, the WM were used to qualitatively predict the BZL. And in order to get the optimal parameters of the WM, the MSE of the MSE values of corresponding to the difference parameters we obtained from the figure 11, we can get the optimal parameters of the WM. That is, for the WM organism, the optimal Landers number in the hidden layer is 10. PSOWM is 10. QPSWM is 9. For the two learning factors, lambda and eta, for WM, the optimal values are the 0.05, 0.0001. For the PSOWM, it is the 0.02, 0.003. For the QPSWM, the best value is 0.04, 0.0003. For the PSOWM organism, under the optimal parameter, the MSE of the blood glucose is 0.48005 micromole each letter. For the QPSO, the MSE values of the blood glucose is 0.35485 micromole each letter. So, and then in order to improve the prediction performance, the novel non-dynamic linkage coefficients of QPS organism were used to verify the availability of the novel non-linear DSC strategy. 4 kinds of different DSC strategies, that is, linear strategy, second-order strategy, quadratic strategy, power exponent strategy were compared. The 4 kinds of DSC strategies were given as follows. For the novel non-linear DSC strategy, that is given as follows, and the dynamic ranges of the 5 kinds of DSC strategies are given in Table 1. And the function profiles of the novel non-linear DSC strategy and the other 4 DSC strategies were also presented in the figure 3. Under the optimal parameters of the novel non-linear DSC strategies of QPSO organism, the MSE values of the blood glucose for the QPSO WM with dynamic DSC strategies that is the 0.3088 micromole each letter. Then, in order to improve the performance of the QPSO organism, the MSE values for the testing blood will compare for the 6 different organisms, which is given in the following figures. From the figures, we can find that for the improved QPSOWM, that is the QPSOWM organism with the novel non-linear DSC strategies were proposed in this work. The MSE of the BGF4 125 testing set blood was further increased to 0.3088 micromole each letter. Okay, that is my presentation for this award. This work was supported by the Chinese National Natural Science Fund, key project of Natural and Science Fund of Jiangxi Province, Young Top-Notch Personal Fund project of Jiangxi STNU, and the project of key Laboratory of Optical Electronic Detection and Information Process of Lanzhou City. That's all. Thank you.